Imagine you are standing in a quiet room. Everything is still. Suddenly the floor begins to move. Not just a little tremor, but a violent, rolling motion. The walls groan. The ceiling cracks. This is the terrifying reality of a major earthquake. It is a force of nature that we cannot predict with perfect accuracy. It arrives without warning, that the ground beneath our feet is not as solid as it seems. For centuries, humanity has lived with this threat. We have built our cities on fault lines, accepting the risk as a part of life. We have watched our greatest structures crumble in moments. The Earth is made of tectonic plates. These massive pieces of crust are always moving. They drift slowly, almost imperceptibly, across the planet's molten core. But sometimes they get stuck. The pressure builds and builds over years, decades, even centuries. Then, in an instant, the plates slip. All that stored energy is released in the form of seismic waves. These waves travel through the ground, shaking everything on the surface. They are the source of an earthquake's destructive power. In places like California in the United States, or vast regions of China and Japan, this is not a distant, abstract idea. It is a constant, looming possibility. Think about what happens to a building during one of these events. The ground moves horizontally, back and forth, but the building, due to its own inertia, wants to stay put. This creates immense stress at its base. The foundation is pulled one way, while the top of the structure lags behind. The result is a violent whipping motion. The building flexes and sways, and if the shaking is strong enough or lasts long enough, its columns and walls will fail. This is the fundamental problem engineers have tried to solve for generations. How do you keep a building standing when the very ground it is built on turns into a shifting, unpredictable sea? Historically, the answer was to make buildings stronger. We used more steel. We poured more concrete. We created rigid structures designed to resist the shaking. This approach is like bracing yourself in a moving car. You are still thrown around, but you hope your strength is enough to withstand the forces. It can work, up to a point, but a powerful earthquake can overwhelm even the most rigid designs. It is a battle of brute force against brute force, and often nature wins. There had to be a better way. What if, instead of fighting the earthquake, we could simply let it pass by underneath us? What if a building could remain almost still while the ground beneath it shakes violently? This is not a concept from science fiction. It is the core idea behind a brilliant engineering strategy called base isolation. We isolate the base of a building from the ground. We create a separation, a kind of buffer zone. This allows the earth to move back and forth, but those destructive forces are not fully transferred into the structure above. This essay will take you on a journey into the world of seismic isolation. We will not get lost in complex equations. Instead, we will use diagrams as our primary tool. You will see how a traditional building responds. Then, you will see the magic of an isolated building. We will deconstruct the technology, piece by piece, so that the core principles become clear and intuitive. In the United States, cities like San Francisco and Los Angeles are built along major fault lines. In China, engineers are now building new hospitals and schools with base isolation. In Japan, this technology is common. New Zealand, Turkey, Italy, Mexico. The problem is universal, and the search for a solution has brought engineers from around the world to the same elegant conclusion. This is not just about preventing collapse. It is about continuity. It is about ensuring a hospital can keep operating right after an earthquake to treat the injured. It is about protecting data centers that run our digital world. It is about keeping bridges open so that first responders can get through. Base isolation offers more than just survival. It offers resilience. It promises that after the shaking stops, life can go on. Let us now build our diagram. On the left, we have a conventional building. On the right, we have our base-isolated building. Now, let us introduce the earthquake. We'll represent it with a large, bold arrow. The ground moves to the right. For the conventional building, the foundation is yanked to the right. The force is transmitted. The building bends and deforms under the stress. Look at the right side. When the ground and foundation move right, the isolation bearings deform. They stretch. They slide. They absorb the movement. The main structure, by inertia, stays almost in place. The building effectively glides above the earthquake. Let's zoom in and look closely at one type of isolator, the elastomeric bearing. It is constructed from alternating layers of rubber and steel. The rubber provides the flexibility. These steel plates give the bearing incredible vertical strength. Some elastomeric bearings have an additional feature, a central core made of lead. As the bearing shears, the lead core also deforms, and in doing so, it dissipates even more energy through heat. This lead core also provides a kind of self-centering force. It does not end up permanently displaced after the earthquake. Now, let's explore a different strategy, the friction pendulum bearing. Imagine a bowl. Place a marble inside it. Gravity pulls it back to center. It consists of two main parts, a concave, dish-like surface, and an articulated slider that rests inside it. When an earthquake strikes, the slider, carrying the building, slides up the curved surface. As the slider climbs, it lifts the building slightly. That is the pendulum part. Lifting the mass uses gravity as a restoring force. This action dissipates energy through friction. Every building has a natural frequency. If a building's natural period falls within this range, it's in the danger zone for resonance. The core strategy of base isolation is to fundamentally change the building's rhythm. This dramatically lengthens the building's natural period, shifting the building's rhythm completely out of the earthquake's high-energy frequency band. While the isolators themselves are the stars, they often work with a supporting cast. One is the damper. Another critical component is what we might call the seismic moat. In the United States, one of the most prominent examples is the Los Angeles City Hall. Engineers chose to place the entire building on a new foundation equipped with 422 elastomeric bearings. The University of Southern California Hospital rests on 198 lead rubber bearings. This design lets the hospital withstand a magnitude 8 quake and remain fully functional. The Benicia Martinez Bridge was designed with large-scale friction pendulum bearings. That movement prevents catastrophic column failure. Japan has long been a global leader. The West Japan Postal Savings Computer Center was put to the ultimate test. The base-isolated computer center performed flawlessly. Not a single cup fell from a shelf. It is widely used in residential construction. Families are willing to pay a premium to protect their homes. The Tokyo Skytree, one of the tallest structures in the world, uses damping and isolation to control its sway. China has increasingly turned to base isolation. A landmark project is the new terminal at Kunming Changshui International Airport, supported by over 2,000 friction pendulum bearings. Driven by the memory of the 2008 Wenchuan earthquake, there has been a major push to build schools and hospitals using base isolation, ensuring that the building becomes a safe haven for children. New Zealand, Italy, Turkey, Mexico. The global spread of this technology highlights a universal truth. Resilience is a shared priority. We began this journey with a question. For centuries, the answer was to fight. Then, a new idea emerged. What if, instead of fighting the earthquake, we could simply sidestep it? The genius of base isolation lies in its simplicity. By inserting a layer of horizontal flexibility, we change the building's rhythm to decouple the fate of the building from the fate of the ground. It is what allows a hospital in California to continue performing surgery, a data center in Japan to keep running, a family in China to shelter safely. It is a technology that delivers not just survival, but continuity. The benefits are clear. First and foremost is safety. This leads to the second major benefit, continuity. It is the difference between a community that is shattered and a community that can begin recovering immediately. The story of base isolation is a story of human ingenuity. It is a testament to our ability to solve problems not with more force, but with more thought. In every city that stands on a fault line, this technology offers a path forward. It is a quiet revolution happening at the foundation of our buildings, one that allows us to live more securely on our restless and beautiful planet.